So in this video, we are going to talk about the boundary layer characteristics. So consider a uniform flow U over a thin, long, flat plate, and assuming that we have a steady and incompressible flow. If we look at the shape here, we have inviscid flow, and then if we are going toward the flat plate, then the viscous flow is going to be more important. So here we have then here we have viscosity in this region, and also here, which is out of that boundary layer, we have inviscid flow. We also call it irrotational. The flow is said to be irrotational out of the boundary layer and rotational here in the boundary layer. And this rotation implies the vorticity, right? And then here we're going to have the laminar boundary layer and the turbulent boundary layer, and we can know it by solving and knowing what is the critical position for the transition. So XCR is the critical position for transition. So if we say that the Reynolds number of X is U, is the U, which is the velocity of upstream, times X over nu, and X is the position along the surface. So let's say that X is position along surface. Then this is how we are going to find the XCR, which is the critical position for the transition. So for the external flow, the Reynolds critical is 5 times 10 to the 5th. And this is the formula for, so this is the formula for the Reynolds number. UXCR over nu, and then from here we can solve it for XCR. Also here, let me just delete that one. This is I write down viscosity, and here if we look at the shape, we can see that gamma, which is the boundary layer thickness. And now for the finding the Blasius boundary layer solution, we are going to use the Navier-Stokes equation, and we are assuming that the flow is viscous and incompressible. So let's talk about the terms in the Navier-Stokes equation. So this one right here, so these two. So these two right here is the effect of the bulk fluid motion, right? So fluid motion. And this one right here, oops. So this one like here is the pressure effect. And this one is the viscous effect. And also there would be another term, but because we said that it's a steady, then we didn't consider that, but we know that this term right here represent the unsteady or steady flow, right? So also if we consider the conservation of mass, and because it's a steady state, so we can say that del V is 0, right? And also we consider that nu is really less than u, and so dx is really less than dy, right? So this is how we can just simplify. And if we simplify this equation, we are going to get the boundary layer thickness, and then this x, we can say that it's at a particular location, right? Particular position. And this one right here, we call it the wall shear stress. And this is the local friction coefficient. And this one is the friction drag coefficient. Right? And all these are valid for a laminar flow over a flat plate. Now let's find the drag force caused by the fluid interacting with the body. So let me just say that find drag force. So for finding drag force, we are going to use the conservation of mass and the conservation of momentum. So if I write down the conservation of momentum, and just one more thing that I think I didn't mention in the in this figure is that if we look at this flow right here over that plate, we can see that the pressure is constant through the boundary layer. So this is also important. So let's say that the pressure is constant through boundary layer, right? The P dy is 0. And if we use the conservation of mass, so we know that 0 is equal to rho v n dA, right? And so because of, here, we can see that UH, right, is equal to U dy, right? And also we can, if this is the control volume, so, and this is the m dot 1, the m dot 1 is rho u a, and a is h b, and b is the depth to the surface. And then right here we also have m dot 2, and then u is we don't have we don't have a uniform u like here. It 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 changed, right? So this is why we cannot bring it out of the integral. So then we have rho u b dy. Yeah, it's changing through y, in y direction. So this is how we write it down, and we know that then the m dot 1 is equal to the m dot 2. So this is for the conservation of mass. And now the conservation of momentum, if we use that and substitute the conservation of mass into it, this is at the end, this is how we get the drag force. This formula right here is the drag force, right? And this formula represents represents the growth of boundary layer, right? And so this boundary layer is increased along the plate, right? So the boundary layer thickness in, del, right? So del increased long plate, and then the shear stress decreases along plate. So this is what we have for the drag force. I said that this is for the laminar flow, right? So let me just write it down. I don't want you guys to forget it. So this is valid for laminar flow over a flat plate. But for the turbulent flow over a flat plate, there is no exact solution to characterize the turbulent boundary layer. So, and we are using some experimental equation that we find through the experiment. So these are like the empirical equation for the flat plate drag coefficient, right? And then this is the critical Reynolds number that we talk about it. So, and let's see what else we have. And also for the, and this is the shape. Also, we are using for the for finding the drag and the drag coefficient. And then we also can say that for the flow, when it's completely turbulent, the drag coefficient, the friction drag coefficient is independent of the Reynolds, because you can see through the shape here, this is the completely turbulent, and all the line is just kind of straight, right? So this is why if, for example, if the Reynolds number is 10 to the 9th, so then the drag coefficient gonna be 0.006, right? And then if still, let's say that the Reynolds number is 10 to the 7, right, which is still in the completely turbulent flow, then the CDF is still the same. So this is why it's independent of the Reynolds number. Oh, and yes, and that's it for the um, for the coefficient of the drag for the turbulent flow over the flat plate. And now let's go to talk about the effect of the pressure gradient. So here the important thing that I want to mention is that the free stream velocity on a curved surface is not constant, and as we can see through that through this figure right here. So it means that the pressure does vary in the direction along the body surface if the body is curved. And then the variation in the free stream velocity, which is UFS, is, I mean, that the fluid velocity at the edge of the boundary layer is the cause of the pressure gradient in the direction. Um, so now why the pressure gradient are important, because the characteristic of the entire flow, both within and outside of boundary layer, are often highly dependent on the pressure gradient effects on the fluid within the boundary layer. So this is why this is important. And so here in this figure, I wanted to show you the separation location, and the separation happens because when the fluid within the boundary layer doesn't have such an energy supply, and then the flow the fluid flows against the increasing pressure as far as it can, and then at some point the boundary layer separates from the surface. So and this is why we have a separation right here, and then this is the zoom of that boundary layer that we have at the separation location.